And then we're going to go to applications of derivatives, so where they are very, very useful. And then we're going to go into a so-called higher order derivatives. All this means is that you took a derivative of a function, but you can do it again and again. So what does that mean? What kind of information those exercises contain? Okay? Good. So let's have a look of what we talked about the last class. So we talked very conceptually in the beginning of the class, and we focused on this idea that a derivative is nothing but a slope of a tangent line for a specific function at a specific point. So this is a definition. You take some small distance h, and you change your argument of a function. You subtract the old value and you divide by h. And then you take a limit as h shrinks to 0. But what does that mean? So we looked at this picture where I pulled out any function, so some function, something related to logarithm, I think. And then I presented this idea that the function changes faster or slower depending where you look at. So if you are at this point of the graph, the function does not increase that much. But if you look at the function here, it increases quite fast as we progress along the x-axis, okay? So the natural way to measure how fast the function changes is to take this so-called tangent line and just draw it in such a way that it just touches the graph at a certain point. For example, the red line right here. Now, the derivative of a function is exactly the slope of this red line, the tangent line. Now, the problem here is that to find the slope of this line, you need at least 2 points on x and y axis. However, we only have 1 point here. We do not know anything else. So this is where this definition of a derivative through the limit comes into play. So what we did, we said, let's focus on this point right here, and let's move a little bit away by some distance that we denoted by letter h. So what it does is that at this point, x plus h, the function obtains value here. So f at x plus h. And then what we can do, we basically get a new point that is on the graph. So we cannot find a slope from one point of this red line, but we can find a slope of a blue line, like this. And then in order to obtain a slope of this blue line, then I need to take a ratio. I need to take this difference, and I need to divide by h. That's a definition of the slope. And then what we do, we shrink this h to 0, so it becomes very, very small. So you can imagine that I'm moving from here back to x. H becomes very, very small. And then what happens, it happens so that this blue line starts rotating and it becomes more and more similar to the red line, the tangent line. So indeed, the slope of a tangent line, the red line, which is a derivative, it's basically the slope of the blue line when h is very, very small, when in a limit it is 0. So this is how this mathematical definition of a derivative conceptually turns into something graphical, and I think it's something nice. So we use these ideas that in order to find the slope of the line, you need 2 points, and we learned it a few weeks ago, and then where to use it apart from having some sort of abstract exercise. Well, this is where it comes to play very handily, because we try to proxy the slope of this line that would actually measure the rate of change of a function with another line that is not a tangent line, but we can force it to be very similar to a tangent line. So that's a conceptual definition of a derivative. And then for a different function, you will have a different derivative. And then for any possible function, you can solve this limit problem, and then you will obtain the derivative at that point. So we did it for a couple of functions, but we're not going to do it all the time. So the idea is to know that all these rules that we're going to repeat now, and the rules that we learned in the last class, they are obtained through solving a limit problem of exactly the sort that I presented in the previous page. So for instance, we talked about the rule where you have a polynomial of degree n. So you have a, which is some constant, you have your unknown x, and then there is a power n, and n is not equal to 0. So then the rule of this, that the derivative of such function is a times n, and then x is raised to n minus 1. So you basically take the power, you subtract 1 from the power, and then the power just goes in front of your unknown. Another rule that we were very quick to figure out was that if you have a linear function, then its derivative is just the slope of that linear function, the slope of a line. Why? Because when we talk about derivatives, we talk about tangent lines. So if you have a linear function is its own tangent line. They completely coincide. So therefore, for a linear function, the derivative is going to be just the slope of that line, just the coefficient a in front of x. Another rule that, again, we were very quick to understand ourselves. Let's say I have a function which is a constant, so it doesn't change with x. It's just some fixed number. Then the derivative of such function is equal to 0, because by definition, a derivative is the rate of change of a function as x changes. But then if a function does not change, then there is no rate of change. Then it is 0. Next, this seemed to be quite challenging, but it was not actually. It was so because the derivatives fully coincide. If you have an exponential function, e to the x, it could be pre-multiplied by any constant. If you take a derivative of such function, then it stays exactly the same as the original function. So when you have derivatives in terms of e to the x, then nothing's going to change. It's very easy. Unless you have something else happening here, maybe this is x squared or some constant multiplied by x, then you need a chain rule, and we will practice this again today. But if there's nothing more, just x here in the exponent, then the derivative is not going to change. Right? And then we have one for a natural logarithm. So if you have any constant multiplying natural logarithm of x, then the rule was that logarithm turns into 1 over x, which is the same as this constant a divided by x. Okay? And then we had some general rules. So these are for any functions. So let's say you have a function f of x, which is defined as a sum of two other functions. Okay? So then the derivative of such function is just the sum of derivatives of those two other functions. So the derivative of a sum is just sum of derivatives. That's very easy, very understandable. Now, the situation changes a little bit if you have product of two functions, right? So this was addition, but this one is a product. So it could be tempting to think that a product, that the derivative of a product is product of derivatives. But that's not the case. We need a bit of more work. This is so-called product rule. So you need to take the first function, u of x, take its derivative, multiply by the second function, v of x, in its original form. You don't do anything. And then you just add the original form, u of x, and you multiply it by the derivative of the second function, v of x. So this is the product rule. We've got to, of course, again, have some examples. Then if we have a multiplication, then we should have a division, and that's the third case, where you have a ratio of functions. So you have u of x over v of x. And again, it could be somewhat tempting to think that a derivative of a ratio is just a ratio of derivatives, but that's not the case. It becomes more complicated, so we need to look into this formula. The denominator part is very easy because you just square the denominator and you forget about it. But in the numerator, you have to repeat what you have in the product rule, but then instead of plus, you do minus. So you need to pay attention here. It's the same as product rule in the numerator, but you need to put the minus sign. Attention. Yes. All right. And then the last one that we talked about, so we finished our last class with the so-called chain rule. And it is called chain rule because effectively we are taking derivatives in chain. So these examples, they are situations where we have a function inside of other function. And then how to take derivative of such function? Well, you do it in turn. So you first take a derivative of a so-called outer function, the g function, then you keep the original inner function inside, and then you multiply it by the derivative of the h function. So this is so-called outer derivative, and then you have an inner derivative. We talked about some tricks how to make it easier, how to spot it, and just how to work sequentially, not to mess it up. So I'm going to start the lecture by just going through some more examples of specific rules and general rules. And then I'm going to talk a bit about applications of derivatives. So how can you use the rate of change of function to answer some questions? And then we see that one very pertinent question is where the function is increasing or decreasing. So it's very easy to see from the graph of a function where it's increasing or decreasing. You just look at the graph and see it yourself. But maybe if you do not have a graph of the function in front of you, and it's very tedious to draw because maybe a function is just complicated. But then maybe it's not so complicated to use the rules that we have to take the derivatives. And then we're going to talk a bit about higher order derivatives. So what it means to have a derivative of a derivative. So what information it contains. So these are the important questions of today. All right? So I would say let's just, again, go through examples, and let's work together. Examples of derivatives. And let's just look at various examples, various rules. Because with derivatives, indeed, this is knowing several rules and then just combining them. Because after all, there is a finite number of rules. But then sometimes you need to use them a bit creatively. So you need to recognize when it's the product rule, maybe it's a product rule within chain rule, and so on. So you need to keep consistent with application of the rules. Okay? So let's start with just a few examples. So let's say we have a function like this. F of x equals 1/2 square root of x. Okay? And I'm asking you to find a derivative of this function. F prime. So prime denotes that this is a derivative. Okay? So here, what I do first is recognizing that square root is simply the same as raising to the power of 1/2. And then we just apply the rule number 1 from the list that we have. That the power goes down and we subtract 1. Okay, so the constant in front, we can just write it again, 1 over 4, sorry, 1 over 2. It's 1 over 2. And then this 1 over 2 is going to go down here as well, because whatever is in the power, it goes down. And I have x raised to 1/2 minus 1. So whatever the power is, as long as it's not 0, we just subtract 1. Okay, so then we have 1/2 times 1/2, 1 over 4. And then I have x, and then I have minus 1/2, right? Because 1/2 minus 1 is minus 1. And it's totally fine to keep it that way. In the exam, if you do the steps correctly, and if you arrive at this stage, it's perfect. I always like using rules of powers a little bit more, and just keeping it a bit neater. So 1 over 4 is 1 over 4, but I can write this as x to the minus 1, and then all of this is raised to 1/2. Because minus 1/2 is just multiplication of powers, minus 1 and 1/2. So that is the same as 1 over 4. X to the minus 1 is 1 over x. And then I have 1 over 2 going on here. And now I can apply 1 over 2 here. So this is 1 over 4, and 1 raised to 1/2, this is just 1. And then I have in the denominator x raised to power of 1/2, which is just square root of x. Okay? So which is the same as 4 square root of x. Right? So you can keep it in the form that we got here. That's totally fine. You can make it a bit more pretty in here. All right. Was this clear? Yeah. So just power rule, right? Whatever power you have, move it down. Subtract 1. In the example B, we have something similar, so I still want us to work with the powers. Let's say I have 2 times x to the minus 1, right? So the power is minus 1, but I can just, again, use the power rule because it can be any number apart from 0. So then I can totally use it. So f of x prime. 2 remains, minus 1 goes down, and I have x minus 1 minus 1. So the only aspect you need to take care of here in the exponent is, not to screw up the subtraction here. That minus 1 is minus 2. So you need to be a bit careful here. Minus 1 times 2 is just minus 2, and I have x to the minus 2. And again, we can keep it that way, or we can rewrite it by using power rules. So it's minus 2 times 1 over x squared, which is the same as minus 2 over x squared. So that is the derivative. Again, we are using the power rule here. Okay, let's look at example C. Let's say I have a function which is, let's say, x squared times e to the power of x. Like this. So this seems a bit more complex. So what would be your suspicion? What rule would you use here immediately? What would you think? Sorry? It's not like that. So what you are saying now that the derivative of a product is product of derivatives, but that's not the case, right? It's true that should we take a derivative here at any point, it's going to stay the same. But it's a product of two functions. So we need to use a product rule. Right? It's a product of two functions. So you need to use product rule. But that is true, that the derivative of e of x is not going to change. That's perfectly fine. Okay, so here, when you have the function where you are supposed to use the product rule, I would say just prescribe the names. So let's call this u of x, let's call this one v of x, right? Because these are the primitives through which we defined the product rule. So let's just give names. So when using product rule, we take the first function, u of x, and we just take its derivative, u of x prime, right? So the derivative of x squared, that's just 2x, okay? And this is, in terms of the rule, u of x prime, so the derivative of the first function. And then we focus on the second one, e of x, and then we just rewrite it. So this bit is v of x. So it's not a derivative, it's a function as it was, original form. And then we add, now we need to write u of x as it is. So that is x squared. And, well, luckily, here where you're right, is that the derivative of this is not going to change. So although this is v of x prime, it looks exactly the same as the original function because that's the rule for the exponentials. So this is u of x as it was, and then we multiply by the derivative of the second function, but it just coincides and it's the same. Okay? So again, now we can leave it in this form. Sometimes for simple questions, it's just easier to simplify it a little bit. So for instance, here we can factor out e of x, because they are shared. Also, this function has x. This function also has x. So it has x squared, but also it's x times x. So it has x at least once. So then we can factor out x, e to the power of x. And this is going to be 2 plus x, like this. And so what I did, I just noticed that this x to the power of x times e to the power of x, it is here, but it's also here, multiplied by one additional x. And then I just factor it out to make it a bit neater. So I factored out this one. Okay. So here, product rule, important. As we had an example, sometimes you do not need product rule, right? So let's say we have, let's have a small example additionally. Let's say I have example B. Let's say I have a function, x squared, and let's say I have 2x plus 1, something like that. Okay? Again, we look at it just from the pure visual standpoint. It looks like it's u of x here, and we can call this v of x. And we can indeed proceed by using product rule, no problem. But if you have a situation like this, product rule is a bit of an overkill, I would say, because you can simplify this function. So here, you can do it, but there is no need for product rule. So you need to be a bit forward-looking again, and just to notice that you can rewrite this as 2x to the power of 3 plus x squared, right? Because I can just take this, multiply by this, and multiply by that. So if I multiply, then I have a much simpler function, and here I can just use power rule here and here, and use the fact that a derivative of a sum is sum of derivatives. So it's a way easier and quicker path to the same answer. You would get exactly the same answer. So I can just write that we use the power rule instead. So we have what? We have f of x equals to 2x to the power of 3 plus x squared. So because it's a function which is given by the sum of two other functions, then we can just use the fact that sum of the derivative of a sum is sum of derivatives. So here we use 2 times 3x to the power of 2 plus 2x. So these are just individual derivatives. Like this. Okay? So it's much simpler. If you want to, I mean, if you look, when you look through these notes, you can attempt taking derivative of this function in its original form, the way I wrote it in the beginning. You can try doing product rule, just for the sake of practicing product rule. And you're going to get exactly the same answer. So it's a good exercise to do no matter what. But when it comes to examples of the nature of C, then you must use product rule, because there is no way to simplify, right? The way, or why, the reason we can simplify this is the fact that we can just distribute, we can just multiply, and we can merge the powers, right? Because we have x squared here, we have x here, meaning that we have x to the power of 1, so that's the same base, and we can just merge the powers to get x to the power of 3. But here there is no way to simplify. So you need somehow to take the derivative of this, and it's a product of two functions which cannot be simplified any further. So you just need to proceed with a product rule. There's no way out. Right? So it's always good to be a bit forward-looking and to maybe simplify before doing something that's not necessarily needed. All right, let's have one more. So that was the example D. Let's have example E. And again, this is going to be a product rule, but within practicing the product rule, let's remember a derivative of a natural logarithm. So let's say I have x to the power of 1 over 3, 1/3, and it's multiplied by natural logarithm of x. Right? So we have a function like this. And again, that's product. So very important, it's a product. And again, there is not really any good way to simplify it. Because it's not that we have everything just in terms of x, in terms of a clean polynomial. We cannot merge any powers, so the best we can do is just use the product rule. So should you use product rule? I always just give names. So this is going to be the u of x, this is going to be the v of x. Right? Just to recognize that it's constituted by the product of two functions. Okay, so again, use the product rule. So the derivative of u of x, we don't look at anything else. We take the derivative of x to the power of 1 over 3 in isolation. So again, quite simple, because we have a power 1 over 3. It's not 0, so we just use the power rule. So we have 1 over 3, that goes down. We multiply by x, and here in the power we do 1 over 3 minus 1, like this. Okay, we just subtract powers. And we just rewrite v of x. This one does not change, we just copy it as it is. So this bit is u of x derivative, and this is just the original v of x. And in here, now we have a second component, so we do plus. And now I need to write u of x as it is originally, so that's x to the power 1 over 3. And now I need to take a derivative of natural logarithm. So my idea behind this very example was just for us to practice the derivative of natural logarithm. And you only need to remember that it's 1 over x. Derivative of natural logarithm is 1 over x. So this one is u of x originally. All of that is v of x prime. That's the derivative of natural logarithm. So here I think we can really spend just a minute simplifying it, because we kept everything very, very open, so to speak. So we have 1 over 3. And then here I have x raised to 1/3 minus 1. So we can just subtract it. So it's x raised to minus 2 over 3, right? 1/3 minus 1, minus 2 over 3. Natural logarithm, nothing can be done about it. It stays as it is. But here we can do something, right? We can do plus, and we can recognize that, well, 1 over x is the same as x to the power of minus 1, right? That's always true. And here I have x to the power 1 over 3. I have x to the power minus 1, so I can just neatly merge the powers. That's quite nice. So I have x 1/3 minus 1, like this. Okay? So this one we can repeat. X to the minus 2 over 3 logarithm as it was. And then I have plus x minus 2 over 3. Right? 1/3 minus 1 minus 2 over 3. And now we can stop here, but we might as well recognize that I have x to the minus 2 over 3 here, x to the minus 2 over 3 here, so I can just factor this out. Why not? You don't have to do it, but I like fixing things until the very end. So I can just factor out x to the minus 2 over 3. So I have 1 over 3 logarithm x plus 1. I have again, this was a product rule, and it's one of these cases where you just cannot really simplify it from the get-go to use something simpler to tackle the problem. Here, all you need to do is just to straight away apply the product rule. And you always need product rule when you have a product of two functions, but one of the functions, if you notice that one of the functions is logarithm, exponential, so something a bit non-standard, then you will need a product rule then, because there is no way to simplify and go around these things. But then the product rule is you just need to admit to the rule. And it's very sequential and it's kind of clear what to do. Alright, so we practiced a bunch of rules, and we can do, so this is example F. We still haven't practiced two things, right? We haven't done quotient rule, so we did product, but we can do the ratio, and then chain rule. That's very important. So right now, I have a function, f of x, that is a ratio of two other functions. Let's say I have x squared plus 2, and let's say I have e to the power of x. Well, so very clearly, here we have a ratio of two functions. So we can call this one u of x, we can call this one v of x. Just to keep track how the rule was written first. And so this one is a little bit longer, so I'll just remind you that for the quotient rule, the derivative is going to be u of x prime, v of x, minus u of x, v of x prime. So just like product rule, but we swap plus for the minus, and then whatever we have in the denominator, v of x, we square it. So that's the easy part. We just square, and that's it. So for this, we just need to follow the sketch here. So we already know what v of x is, what u of x is, so now we just need to match the terms and take the derivatives individually. Okay, so first in the numerator, we have u of x prime. So what is the derivative of this? X squared plus 2. What is the derivative? Yeah. Exactly. Because if you add something or you subtract something, it's just a constant. It doesn't matter. The derivative of a constant is always 0. That goes away. So we have 2x, right? And then we have v of x, as it is. So that's e to the power of x. We have minus, and now u of x as it is, x squared plus 2. And now, again, very nice. So it's really nice to take derivatives when you don't need to do anything. Because e of x derivative is always the same. So that's just e of x. And then what we do, we simply divide by ex e to the x squared. Okay, so we are basically done. We just apply the rule and we got what we were supposed to get. We can just simplify it a little bit. So what about we have 2x e to the x, then let's say I have minus, or we can keep it that way, sorry, can keep it that way, but we can do something else. We can really simplify this. Notice that we have e to the x here, and we have e to the x here. So what we can do, we can write e to the x, so we can factor out e to the x, and we have 2x minus x squared plus 2, right? And here we have e to the x squared, okay? So I can cancel e to the x, and I can cancel it with this one. Because here we have e to the x, and we have e to the x squared. So square just cancels out. And now we can just fix this one, because we have minus x squared plus 2. So we can just open the brackets by recognizing that we have a minus in front. So this leads to, let me remember, 2x minus x squared and minus 2 e to the power of x, like this. Okay, so again, this was just a quotient rule. You have a ratio of two functions. Just prescribe, let's say call this one u of x, this one is v of x, and then in this case we just do the product rule in the numerator with a minus instead of a plus, and we need to square the denominator. And then in this very specific example, we managed to simplify it by factoring out v of x and just canceling it against e to the power of x squared. So before I go to the chain rule, now we are supposed to do that, just wanted to do two extra things. First one, the derivative of this does not change, right? The question is why this does not change. Why? So this is a special case of another rule, actually. For any exponential function with any base, any positive base, for any exponential function, f of x equals a to the power of x, right? Where a is any positive base. For this example, we just chose very specific base e. So for any exponential function, the derivative is given by a to the power of x times natural logarithm of a. So had this been 5, let's say this one is 5 to the x, then the derivative is 5 to the x times natural logarithm of y. Right? So there's a little new rule for any exponential function. But now this very nicely works with e to the x. So when we take a derivative of an exponential function with the base e, what we are doing, in fact, we are applying this rule, and we do have e to the x times natural logarithm of e, right? So this comes straight from this rule. But do you notice that this is just 1? So natural logarithm of e is just 1 by the rules of logarithms. Logarithm of 1 is 0, logarithm of e is 1. Because logarithm of e tries to answer the question, to what number I need to raise e to obtain e again. So that's just 1. So indeed, the nice fact that the derivative does not change basically comes from this more general rule that applies to any exponential function with a positive base. But when you use it on this very specific choice where the base is e, then very nicely the second component collapses to 1 immediately. So that's one quick fact that I just wanted to take some time to explain, should you be wondering. And the second one, very quickly, and I think after the break this is going to come in handy solving the chain rule, alternative notation. Especially if you looked at the book, there are several ways how to denote derivative. So derivative could be denoted as we looked at, prime, so f prime x, or any function. Or alternative way to denote derivative, that's just another way. It means exactly the same. We need to do the same thing, apply the same rules. df dx. That's another way to denote derivative. This means, in the numerator, this means a small change in function, and dx means a small change in the argument, and we take ratio. Small change in the argument, like this. So this notation literally mimics the definition of a derivative. Because we take x, we move a little bit from x to x plus h in the denominator, and then we take the difference in the denominator. So this mimics the definition. It literally tells you what the derivative is. This notation. It literally tells you that you have a function and you have a small change in the function because you moved the argument a little bit, and then you divide by that small change. Right? So this is just a shorter way of saying that derivative is a very small change in the function over a very, very small change in the argument. And usually this is very popular, but this definition is used when you look at a bit more advanced mathematics, because it tells you what's exactly going on here. But I think for us it's going to be very useful. So after the break we're going to do the chain rule, function of a function, and this notation is going to be extremely useful to understand what is going on. So let's take a break now.